All right, so let's get started. SLA has been a very interesting topic, at least at Yahoo. And we operate, in our team, the Hadoop team at Yahoo operates Hadoop as a service, as a hosted service for the rest of the company. And pretty much, if not all, a large part of our business runs on Hadoop. And this has been a topic which has increasingly come to picture, like customers are demanding SLAs. And there isn't really an SLA button somewhere in Hadoop saying, okay, schedule my jobs with this SLA, at least not yet, right? So that's the motivation behind the talk, to understand SLA holistically and the factors that impact it and what can you do about it. So with that, let me introduce myself. My name is Sumeet Singh, and I manage products, the big data Hadoop platform products at Yahoo. My co-speaker is Nathan Roberts. Nathan is a senior architect with the core Hadoop team at Yahoo. He's been with Yahoo for 8 years, and before that, 17 years with Motorola, so really deep in the systems space. Let me outline an agenda as to what we intend to cover here. So we'll give you a really good overview of the scheduler itself and the job scheduling in Hadoop, because I think understanding that is critical for even moving towards this notion of SLA. And since we use Capacity Scheduler at Yahoo, we've been using it 10 years now, we'll dive deeper into that and talk about that in sort of detail. We'll then talk about the queue management philosophies and how you think about managing queues, all the things around queues, because queue is the basic capacity abstraction in the Capacity Scheduler. We'll then talk about how you go about managing SLAs today and where things are headed. And then we'll open it up for Q&A at the end if you have time. Okay. So let me give you a context for where the processing comes from, where the compute comes from on the Hadoop grid at Yahoo. So we have three primary data processing engines today: MapReduce, Tez, and Spark. These three, MapReduce in large part is what contributes to most of the compute today, and increasingly Tez and Spark. These three are primarily responsible for pretty much all the compute. And then there's a variety of tools on top, such as data management, Pig, Hive, and some of our machine learning applications that's actually driving the compute through these execution engines. Okay? And then we schedule roughly 60 to 70% of all our compute through Uzi on the platform. So we're not talking about HBase or Storm here, because those are separate infrastructures for us. And the compute on the platform is growing rapidly. As you can see, in the last, I would say, 2 years has nearly doubled. So this is one way to look at compute, which has worked okay since it was all MapReduce, the number of jobs. So we're now roughly at 33 million jobs a month, and that's a staggering number. And that's the number why the notion of SLA is becoming increasingly important. With that, let me hand it over to you, to the presentation to Nathan to talk about scheduling in detail.
Thanks, Sumeet. Okay, I'm going to give a little background on the Yarn architecture, just a little bit, so that we're all kind of using the same terms and you'll understand some of the things that come along further in the presentation. So this is a slide on the kind of the architecture of Yarn. At the top, you have the resource manager. He understands what resources the cluster has. He knows what applications are requesting. That's where the scheduler functionality lives, so he knows how to prioritize resources to particular applications. And then second, you have on each of your compute nodes, you have a node manager. As his name implies, he kind of manages the node. So he knows how to launch containers there. He knows how to monitor those containers. And when they're asked to be removed, he knows how to clean up the containers. And then third, you have an application master. So this is the application-specific logic that gets started for every application. So you have a MapReduce version of this. You have a Tez version of this. Any type of computing engine will start as an application master. That application master then knows what types of containers it wants. It knows it needs memory-heavy containers, or it knows it needs CPU-heavy containers. It knows what to request from the resource manager and at what time. And so, for example, for MapReduce, it first asks for map containers, and then it eventually will ask for reduce containers. And then finally, I've used the word container probably 5 times already. It's basically the unit that Yarn uses for bundling resources. So you could have a container that's so many gigabytes of memory and so many cores of CPU, or you could have, it's basically a bundle of resources that it uses to schedule with. So the scheduler functionality I mentioned in the resource manager, it's pluggable, which is very nice. It allows you to do it allows you to use different schedulers at different times. There's 3 basic ones there right now. The default is the FIFO scheduler, which is mainly for development and testing and experimentation. It's basically your straight first in, first out of the jobs. There's also the FAIR scheduler. The FAIR scheduler was born to kind of try to be fair with applications and resources. So you have a pool of resources, you have applications that are running in that pool, and you want to give resources kind of out fairly to the applications. This is really good for small jobs because otherwise they could get stuck behind a much larger job, and when all they needed was a container or two to finish in no time. The FAIR scheduler is capable of using excess resources in the cluster, so it can give them to other pools temporarily. When it needs to take them back, it can preempt them from other jobs. And then also you have the capacity scheduler. As Sumeet mentioned, that's what we use at Yahoo. We've used it pretty much from the beginning. In this case, jobs they're submitted to queues. The queues are FIFO-like. And when I say that, by default, they're FIFO, but there are reasons it won't act in a FIFO way. For example, it wants to try to be, you can configure it so it tries to be fair to the users that are in that queue. So in that case, it may skip the guy in front of the queue and give the resources to somebody further down the line. Same thing as locality. Hadoop and MapReduce, if you remember, is all about bringing the compute to the data, right? So it may skip people in the front of the queue in order to get better locality in the end. And then queues are ordered according to their how far you are, how close you are to your capacity. So capacity scheduler tries to guarantee you capacity per queue, right? But the further you are away from that guarantee, the higher priority your queue is. So that's kind of how it determines where it's going to give resources to. And then like the FAIR scheduler, excess queue capacity can be given to other queues, and then it can be taken back if necessary using preemption. So, like I said, the scheduler's pluggable, which allows for a lot of experimentation. So a lot of research teams and universities and folks like to experiment with different scheduler things. And so a lot of really cool features have come out of that. Right now we use, and resource awareness is one of those. So memory and CPU, the scheduler already understands. Some of the things that people are looking at is also dealing with disk as a resource or network as a resource, because if you get those wrong, it can really slow down a node. So it's more about isolation, right? Memory and CPU, you can isolate that much, and then you want to isolate even more and say, this container can only use this much disk, or this container can only use this much network. Locality delay is a way of waiting for locality to show up, so kind of delaying scheduling so that you get better locality. However, there's a trade-off with that, because as you do that, like I said, you're skipping people in the queue in order to get that better locality. So there's trade-offs. And with a lot of Hadoop, there's always trade-offs, and so a lot of people like to study those kind of things. Dynamic priority, so we have this a lot of times in what we call catch-up mode. So we've had a planned maintenance or an unplanned maintenance, and we need to catch up, right? And so there can be cases where you want to raise the priority of specific jobs. And so being able to dynamically adjust the priority of jobs is something that's being looked at. And straight up deadline constraints. So if you have a very specific deadline for a job, it'd be nice to be able to specify that somehow, either by a specific time or relative times or whatever, but that's a very common thing that people are looking at. And I gave the references there. So question a lot of people always ask is, which do you pick, the FAIR scheduler or the capacity scheduler? They're both very capable. They kind of started, they started in two different places. One was very focused on fairness, and the capacity scheduler was very focused on guaranteeing that you have capacity. But that kind of left a big hole, a big place in the middle, right? So they've kind of converged a lot, and you can do most of the same things with both of them. The fair share started with the concept of fairly allocating, and like I said, the capacity was around guaranteeing capacity. One of the things that we use in the capacity scheduler is label-based scheduling. So we have use cases where we want to partition our cluster. One concrete example is we have nodes, which we call big memory nodes, but we give them a label, And we want very specific applications to run on those nodes that need that big memory. If you let Hadoop or let the capacity scheduler just manage that by default, he'll end up fragmenting those large nodes with other tasks, and you won't be able to get the large memory that you need. So that's an important feature that we use. And then also, the fact that these two schedulers are kind of converging has led the community to start these types of JIRAs where they're going to have policy-driven scheduling. So I can have a queue where I really tune things so that it's very fair. And then I can have another queue that I tune so that it's very capacity sensitive. And so it's basically bringing a lot of that functionality together. So then instead of picking one particular scheduler for the entire cluster, I can pick the policy on different queues. So we're really looking forward to that. And then we use the capacity scheduler. It's designed really well for multi-tenant applications. We've always pretty much been multi-tenant. Almost all of our clusters are multi-tenant, so that leads to interesting sharing problems of resources. We want to maximize our utilization, so the capacity scheduler does allow you to kind of steal resources from other queues, any excess capacity, and we want to do that as much as we can, right? We don't want clusters running at 30% utilization just because every once in a while we have to run at 100. So we want to run, at high percentages as often as we can. And then you have to have safeguards in your schedulers so that if, for example, user comes in with a new application or a new version of his application or his input data set changes all of a sudden to the point that he's taking over the entire queue and then no one else is getting any work done in there. So you want some safeguards for that type of thing. And then, as we'll talk about more in detail later, everything is abstracted through the concept of queues, and those can be hierarchical, and we'll get into a little bit of detail of that. So resources tracked by the capacity scheduler. Right now, this is mainly memory and CPU. Memory was first. CPU came along, I don't know, in the last year or so. We're using both. We have been for at least 6 months, probably a year. There have been a couple of hiccups along the way, but we're pretty much there now. And when you have two resources, one resource is kind of easy to think about, but when you have two, it gets interesting. It's like, which one is more dominant in this case? And so there's this concept of a dominant resource first calculator that's used to figure this out. And it basically made it easy to kind of treat two resources as one, and you can drop it, you were able to drop in that functionality pretty much without too much trouble. However, when you think about it, there's like two resources now, right? So there's kind of two constraints in the system. I have a memory constraint and I have my CPU constraint. If I want to run something, I need to meet both constraints. Therefore, utilization is kind of going to go nowhere, but it's going to go down some, right? There's kind of no way it's going to get better. So that's one of the things we have to make sure that we understand and do the right trade-offs. Now on the CPU side, you can also do C group isolation, and we do that as well, and that becomes very important and actually lets us kind of get that utilization back up again, right? Because previously you weren't sure whether this container was going to use 1 core or 10. He could use all the cores on the box, and all of a sudden everything on that box is running 1/10 the speed that it was before. So C groups made it possible for us to make sure that he said 1 core, that's what he's going to get, and I'm going to keep him to that if the machine gets busy enough. So that's been very important. On the right side, you have to do some analysis and figure out, how do I set my container sizes appropriately. And for MapReduce, that can be trivial in some cases. All the containers run, they kind of are very consistent in their size. It's pretty easy in that case. But then you have, all of a sudden, data skew comes along, and for some reason, your MapReduce grows to 5x of what the other ones are. Now, all of a sudden, you've got to set the size for your application at the largest kind of common denominator, and that's not what you want, because all the other thousands of tasks are wasting all that memory, right? So then it's an analysis that you have to keep doing for your applications to make sure you stay optimized. And then same thing with CPU. CPU is a little more forgiving because if you mess it up, it basically runs a little bit slower. Memory, you screw it up and then the application doesn't run. So that's at least a good thing. And there's just some kind of hints there where you can, based on CPU time spent over how long the task run, well, that's kind of that can be a good estimate on how many cores I need to request. That doesn't always work, right? Because, obviously applications don't run with a straight line of their CPU requirement. They'll have very high periods and then they'll have lulls in their period while they're waiting on I/O or whatever. But it's a good starting point. And then, so tying back into SLA, some of the features that really help you meet SLAs. This isn't really a yarn feature as much as it is an execution engine feature. So for example, MapReduce supports speculative execution. TES supports it. Pretty much all of them have to if you want to run at a predictable time, right? And so what is speculative execution? I'm running a lot of tasks, and for some reason one of them tends to be running slower than the others. So what do? I just launch a copy of it. Whoever gets done first, he wins. So that's very good at dealing with slow nodes in a cluster. We run clusters that are multi-thousand node clusters, and at any one time, I can guarantee you there is a node that is running slow. So in fact, we use this feature for finding those slow nodes. So we send out reports on how often nodes are losing speculative execution, and that sends that node into automatic fixing processes that we have. So it's good. It's not only good to keep jobs running consistently, it's good at finding slow nodes and getting them out of your system. Preemption. So like I said, we want to get our utilization up. The only way you can do that is let other queues use capacity that you were supposed to be guaranteed, right? So I'm kind of donating it to them. I have to have a way to get it back. I can either just wait for the task to finish, which is fine if your tasks are churning fast enough and I can get my capacity that I'm supposed to be guaranteed. A lot of times that doesn't happen. There are a lot of jobs that will run multi-hour tasks and I just can't get it back. So preemption is a way to say, you know what, I need my capacity. I'll give you like a minute or so of grace period and then I'm taking it. And basically it will shoot the task and take the capacity back. Downside is I'm running that task and he was doing work and then I took it away from him. So he basically has to start over from scratch on that particular task. But you need to be able to do something like that. So the node label feature is also another one that I already previously mentioned a little bit, and I'll use that example I was using before with the big memory nodes. If you let Hadoop just do this, it can kind of handle it. I have a job that requests almost all the memory on a large memory node, for example. He will place a reservation on that node. Hadoop will wait, or Yarn will wait until all of the resources free up from that node, and then he'll give it to you. But that can take days if you have long enough running tasks, right? So node labels is a way of saying, I have an application, in my example, that needs a lot of memory. I have a bunch of large memory nodes. I label those nodes that way, and then that application runs in a queue that can only run on those nodes. So it's a way of, if I have an SLA with that type of job, that's the only way I'm going to be able to do it. And so in this example, it's kind of showing that this particular queue can access those nodes. The second queue there can access a different set of nodes. And this feature continues to develop. It's pretty basic right now, and it's basically partitioning your cluster. So I have my large memory nodes, I have my other nodes. What you really want to do is to be able to share those large memory nodes when there's nothing else going on, and then be able to take that resource back. And there's a lot of people working on that type of functionality. So queues, we're going to talk more about kind of the queue nomenclature and how we lay them out to help guarantee SLAs, but I'm just going to quickly go over some of the key configurables that are within the queue that matter when you're talking about SLAs. So they're highlighted there in bold, but they're kind of covered on this particular slide all in one shot, so you didn't have to really remember all those. So capacity is the key one. This is what the capacity scheduler is trying to guarantee. So all the capacities for all the queues add up to 100% in the cluster. So this is what he's trying to get you. And you can set up your clusters so that, that I have absolute guarantees. And that's by the next one is the max capacity, which is the hard limit for the queue. So in this queue I have drawn up here, the capacity is at whatever it is. The max capacity is somewhere further. And it's basically saying, I'm going to try to guarantee you capacity. And if you want to grow beyond, I'll let you grow to a certain point. And that certain point is max capacity. If you want to make sure that all your capacities are always guaranteed, then you don't do the max capacity. You basically keep them the same. And then there's a couple of user limit things. So user limit factor is a hard limit for the individual users within the queue. So this is a way of saying I have 10 users in the queue. I don't want any of one of them to take up any more than a certain amount of the queue. So in this example, I think I used 150%. So in this queue, a user could not use more than 150% of the capacity. That's a pretty high number. A lot of times you wouldn't go quite that high. but it keeps him, it's the higher end bound for the user. Now on the lower end bound, you want to be able to make sure that you get users a specific amount. So if you, and this is where it kind of gives you a level of fairness, right? I have 5 users in the queue. I want to give them all a certain percentage of the resource that's coming to that queue. I do that by setting the min user limit %, and that will try to guarantee him a certain level of the resources that are coming to that queue. Once you get above the minimum user limit %, the scheduler tries to evenly distribute between other users in the queue. So in my opinion, this is like one of the most confusing configurables that are in the queue. So I got a slide just for that one. So min user limit %, kind of the setup here is that I have 3 apps in the queue, FIFO. So app 1 came in first, then app 2, then app 3. They were all submitted by different users. So we got 3 different users and 3 different apps running. And so app 1 was, like I said, first in the queue. So he's the one the scheduler is going to try to give resources to first. So the min user limit % here is set to 25%, and I've drawn some containers down there in the lower left and so I'm equating 25% to 3 containers just to kind of make this easy. And then all applications are initially requesting resources. So applications can be running and not requesting anything, but in this case, I'm saying they're all requesting. Usually when you first start up, obviously you're going to request resources, otherwise you're not going to get much done. So this is kind of an initial condition. So like I said, it's basically FIFO until you hit the user limit. So as you see, it's like giving 3 resources to A, then 3 resources to B, and then 3 to C. So it's effectively hitting their user limit, trying to make sure they give that, and that's FIFO until you get that done. Now, we've reached user limit, so what happens next is it's going to evenly distribute among all the applications. So you can see in this case how it kind of went from A to B to C and then A to B to C. And then after you get, if user A stops, or that app stops requesting, so he's done now, maybe he's waiting on, I don't know, a phase of his processing to finish or whatever. Now user B and user C are still requesting though, so now it's gonna stay even between everybody that's requesting. So now it's giving the resources evenly between those 2 applications. And then finally, A can come back. He's like, he finished waiting and he's at his next stage of processing, so now he needs more resources. And then so user A becomes favored again because the scheduler wants it to be even. And since he's first in the queue, he's going to offer it to them, and that application will take them. So that's kind of how min user limit % works. Now Sumeet's going to talk some more about our queue nomenclature and how that applies to SLAs.
Thank you, Nathan. So I think that was a useful overview of scheduling. As you can see, the scheduler itself provides lots of bells and whistles for you to manage SLAs, and understanding that is important as you set up clusters that are typically multi-tenant. But you could do a lot beyond that, beyond what scheduler does, and I wanted to share some of the thoughts or best practices that we're seeing around managing SLAs. So one is the nomenclature itself, the queue setup itself. And a very convenient way to set up queues is by business units, because business queues are, as I said, abstractions of capacity, and you want to manage CapEx typically when the clusters grow, right? So the BU level abstraction is a really convenient way to set up queues and carve out capacity in the cluster to business units. The other common way to carve out cluster is by initiatives or projects, right? Depending on what apps do you run on these clusters, you can carve out your queue by the initiatives, or you can take a hybrid approach. And a lot of these setups may or may not have hierarchical queues, and what I mean by that is the sub-queues within a queue, right? So for example, initiative 1 has 2 projects in the last picture. So these are the common ways to set up queues. Let's look at the job behavior in a queue. So this is from one of our clusters, and it's just looking at the jobs as they're executing in the queue, some random queue. What we tried to do was actually decompose this for extracting out any seasonality or commonality that we see, any pattern that you could see in this, and then look at what is the amount of randomness in this queue. So what would you see is that there's very little seasonality in this queue. And this is a production queue which is scheduled, no human touches it. What it means is that you ideally would think that this should be predicting in a very seasonal way, day after day. And this is done for over a period of time. But it doesn't. There is very little seasonality and a lot of randomness, despite it being a production scheduled queue, right? So you can easily conclude that in database applications, most queues would exhibit a really high degree of randomness. despite how hard you try to keep it sort of consistent. So a good way to think about queue setup then is to keep the BU notion, because that allows you to do a lot of different things. One is, the set up CapEx processes in the company, set up metering, potential automated onboarding of tenants onto the clusters. And BUs can manage the capacity within the cluster by themselves, right? So among their initiatives. And as you think about the initiatives and you launch them on those clusters, given how these queues behave in typical data applications, one of the best things for you to do is to actually take out any ad hoc work or random work out on a separate queue, right? And let the scheduled job, the seasonal jobs run on the primary queue, which I'm calling here a scheduled queue. And you could make the ad hoc queue preemptible. So really set low absolute capacity, high absolute max capacity, and have that queue be preemptible, which means that as scheduled jobs need capacity, it'll take it from the ad hoc queue, right? So that's one of the best ways to set clusters up. And of course, you can have some ubiquitous cluster queues across all your clusters, and all your clusters can look exactly like this. And you can manage a lot of sort of extra capacity, headroom, whatever you want to call it, in the default queue. Default queue also doesn't require you to specify queue name when you submit jobs, right? So you typically do mapper job queue name. You don't need to do that. The other aspect of managing SLAs is that predicting compute capacity needs in advance is really hard. So this is one data point, although dated. The orange line actually is what people were looking for initially. That's what they onboarded for on the clusters, and the blue line is what they're actually consuming. And you would see that there's really no correlation between what people asked and what they actually ended up consuming after a while. What this means is that, and again, there are a lot of factors that go into this. I won't get into that, but it's hard to predict compute capacity in advance. So what can you really do? One thing you could do is try and estimate your compute as accurately as you can. Do test runs on sample data sets. So this is one example where it's a very simple pig pipeline. Let's say you have 3 stages, 1, 2. Stage 2 has 2 parallel leaves, and stage 3 is in sequence. And you look at what you ended up consuming in terms of mapper memory, reduced memory, as well as the sizes of mapper and reducers you launched, the time these mappers and reducers ran for, and also add in the shuffle time over the network. So there are some tips I've left here. And again, this will be very different for your situation. But looking at the counters and job logs, you can actually get this information out. Then, based on your SLA requirement, so in this case, let's say my SLA requirement is 6 hours, you can take these stages and the time these stages are taking and extrapolate this test data set or sample data set to your actual data set that you anticipate processing. Okay, and then you can accurately estimate, well, it won't be accurate, at least you can estimate what your compute need may be, right? So that's one way to go about estimating compute need. So then you should also observe the queue behaviors. This is one example, again, very recent, very real, from 1 week sample. If you look at the aggregate cluster utilization, you don't really see a pattern. This is a production cluster, not a lot of people touch it. And if you look at 2 particular queues that I extracted out and their behavior, you would see that this queue is actually getting starved of capacity, right? It's always above its absolute. It's always going to this notion of 100, 200% utilization. It's good. It's really good for CapEx. It saves you money, but it might actually not help you meet your SLAs. So monitoring the queues and your capacity consumption over a period of time is really important if you're not doing that. And believe me or not, there will be very little pattern that you could extract out from any of these queues. That's typically how data applications behave. Then, typically, there are lots of factors that impact SLA, and one is this change in project itself. You would have new projects coming in, your projects moving within queues or BUs. You would have new users come to those queues. You would have users withdraw from those queues, or you will have bad users in those queues, and they all impact SLA. There's not a lot you could do about that because, as I said, the platform is about offering service. So the only thing you could do is plan, measure, and monitor for consumption. Then cluster downtime can actually also impact SLAs in a pretty big way. Thankfully, there is rolling upgrades now, as well as HA, so you don't really need to bring your cluster down, and most of the rolling upgrades are work preserving, so you can continue and monitor the impact on SLAs. And then finally, we did talk about catch-up. This is when the data arrives late or something else happens, or two data sets show at the same time that were supposed to show 15 minutes apart. You need to catch up, right? And that's a very tricky situation, so you actually need to know what queues to suspend, and how to shift capacity from one to the other to let the critical jobs catch up. The other, as I said, so measuring compute consumption is really straightforward. One of the standard notions we use is GB hour. And it really hones in this idea that the mappers or reducers, you ran the sizes of those, the memory or CPU sizes of those, the container sizes, and how long you occupied those containers for. So much like the electricity bill in kilowatt hours. So you have GB hour. And then again, you can look at logs and either the RMAP summary or the map reduce job logs before and extract out that information really easily. And the jobs are now really organized. So memory seconds and vCore seconds will give you the memory and CPU consumption for the jobs. And again, measuring this over time is critical. As you could see again from a real cluster, just in few days apart, you can see how the consumption pattern has changed, and nothing else has changed, really. It's just that they're processing a lot more data now, and they didn't plan for that capacity, okay? So this can, again, lead to SLA misses. And then measuring and going further to this theme of measuring and reporting SLAs will show you yet another example of why it's important, and there isn't an SLA button on Hadoop. This is, again, a dominant user of 7 users in a common subqueue. This subqueue has those settings, those 4 settings we keep talking about. And this user, this dominant user in that queue of 7 users is submitting a large number of jobs in thousands every day, right? So about 20, 22,000. And there's a large variation in the amount of jobs he's submitting to these queues, despite that he's doing the same stuff every day. If you measure the resource consumption of a very small fraction that is very predictable, in advertising, there's this concept of supply. So it's actually summarizing the ad supply, this particular user, every 15 minutes. So you really have only 96 jobs a day. So out of that 22,000, I'm extracting 96 only, and looking at the variability in resources that that job takes any given day off of those 96 jobs or over a period of time. And you can see the variability. It's a real standard job, but look at the resource consumption variation. And then if you look at the time it takes for that job to complete, again, there's a great deal of variation or variability or randomness, as you could call it. So, you know, in situations like these, measuring and reporting SLA is really the only way for you, despite that you could do other things. So you could measure it at stages, at individual jobs, or for the entire pipeline. And one good practice is to actually tag your jobs or name your jobs properly so that you could do this reporting. The other is that you could pass in arbitrary configurations or parameters to your jobs, and then you can read those parameters back when the jobs are finished. 3 or 4 parameters can do the job, like some sort of a pipeline ID, an instance ID, the start and the end of the pipeline, right? That can do the job, and you can measure your SLAs in terms of job completion times. Uzi, since, as I said, most of our pipelines are scheduled through Uzi, and this was one of the most asked feature, we implemented something called as SLA dashboards about a couple of years ago, so this works fairly well. And it tracks start time, end time, as well as whether the duration was met or missed, right? So on start, end, as well as duration, it will give you a met or miss as you set them. And you can track the stages at any point in time of where the pipeline is in terms of processing or guaranteeing SLA. And you could look at it in different ways. So this is the SLA dashboard, and as you can clearly see in this case, I have a miss here just based on the start miss. So it's both missing the start as well as the end time as to when it was expected to start and when it was expected to finish. And then you have graphs as well that can do the same. So this is a really important topic, and as you can see, there's a variety of effort underway in the community around it. Some of these JIRAs are particularly interesting, like reservation-based scheduling, which allows you to sort of set reservation for resources based on your expected completion time, so that if you're not in rush, Yarn can actually rush the others who are in rush and let them meet their deadlines for SLAs. There is in-queue priority, so we talked about preemption within the queue, and now we're talking among the queues, and now we're talking about prioritizing jobs within the queue so that people can actually get ahead of others. There is also efforts around federation, so managing tens of thousands of nodes across federated Yarn clusters. And then Ethan talked about 3306, where you actually define per queue policy, so really differentiate queues based on fairness and other factors. And then there are lots of talks on this topic. If you were interested to explore further, I think there's definitely a Yarn talk that you should go to. Reservation-based scheduling is new, so they're presenting here. There's another talk which is similar to ours called Enable Diverse Workload Scheduling in Yarn, and then node label features we touched upon. Right. So with that, I think we have 4 minutes, 5 minutes, or even longer for questions. Yeah. So the question is, do you set your queues differently for different applications? So there's a queue for Spark, there's a queue for MapReduce, and there's a queue for Tez. No, we don't. The applications go through the same queue. In fact, one of the charts I showed you, that was taken from the same queue, and you had both MapReduce and Tez in the same queue. Okay. Any further questions? Could you use the microphone?
I mean, if multiple application goes into the same queue, are they still fair sharing on the resource
I'm sorry, I did not understand the question. It's echoing.
I mean, if you're having more than one application goes into the same queue, the resource allocation for those applications is based on the fair sharing rules, so it's kind of like first come, first serve.
So we use the capacity scheduler, so it's going to try to mainly manage around capacity, but there will be some fairness if multiple applications are submitted to the same queue. So for example, to try to get locality to be better, it'll do that. Or also if they're submitted from different users, it's going to try to make sure that multiple users are getting the same, the same level in the queue. If it's submitted by the same user, then it's pretty much going to be FIFO minus, locality delays that it'll put in.
Are you guys planning to use the reservation-based scheduling that Microsoft did?
We don't use it yet. We want to take a really hard look at it because it's a very interesting feature. We've just now started getting preemption kind of to a stable enough state that we can use it, and it depends on being able to do that.
So is there any initiative to create job or query signatures so you can enforce SLAs much better?
What was that? Sorry.
Like a query signature for job signature that kind of captures the characteristics of the job, so you can enforce SLAs much better in terms of resource allocation. Is there any initiative like that? Or
so track workloads in real time and then adjust
and then
scheduler.
Yeah, and then save the sort of the characteristics. That way, if you have to rerun the same job, you don't, you can just say, hey, the last time it ran so much, so I can just.
Yeah, so you could look at like when I showed you the variability. It's the same job that runs on the same data set 96 times a day. It shows different time and different resource consumption all 96 times.
But the reservation feature the goal of it is to let you do things like that, right? Monitor the job over a period of time. If it's very regular, then I can set up my reservations based on that regularity, right?
To me, it seems like it's more measuring and monitoring rather than enforcing
Logs, I think logs are really rich, and I don't know if you mine logs, but logs will tell you everything that is going on. So you could extract a lot of intelligence out of these logs and apply it back to both your capacity, the configurations on capacity scheduler. You could also think about, spacing your job start times. You could also think about a variety of different things. Maybe put more capital, more servers in the queue, more capacity in the queue. But I think that is key. Even if you had reservation-based scheduling, you still need to measure to figure out how much to reserve. I think it's really critical.
A quick question. So the user limit is a queue-based or cluster-based?
It is queue-based. It is per queue.
Queue. So is that fair? Users submit more jobs to a high capacity queue. I mean, the queue with the user either has a labor, probably with the more memory. Some nodes with the more memory in the queue, and the other queue has less memory. So in the case, so from the user point of view, it's not really fair. Sometimes.
It's not complete. Yeah, it's not trying to be completely fair within the queue, if that's what you're asking. I mean, it's trying to guarantee them a certain percentage of the queue, and then after that, just trying to spread them evenly between the users within that queue. If that makes sense.
Quick question. Are there any thoughts around controlling the workload based on the type of workload coming in? If it's a small trivial queries or workload is coming in, I control the concurrency based on the type of workload. For example, if the small set of queries coming asking for 2 to 5 containers, give them 100 concurrency, and put the high cost jobs with asking for thousands of containers, give them 5 concurrency. Are there any thoughts around in managing that kind of a work?
So a cost-based scheduling.
Yeah.
There have been research, like we showed you on, where you look at your current cost and then sort of delay yourself because the cost of running a job today is too high versus the cost of running a job a little bit later, maybe low. So you track your cost and say, I'm only committed to this cost, and I'm going to schedule my jobs or queries based on that cost. That's not in practice, though. Like nothing like that is in sort of production, so to say. What you could do is meter yourself. So metering is easy, as I showed you on compute consumption, and back off. So metering helps a lot with that, like chargeback models. So I'm hearing about chargeback models being built into Yarn. But one way you could do it yourself is through logs. It's just that it's going to be a little late. That things are already happening, and then you're looking at the logs and adjusting. It's not that, no application does it that dynamically. But with the chargeback model being built in Yarn itself, you could do cost-based scheduling. It will enable that. So there have been thoughts there on that topic for a while, but it's not in practice.
I also think different execution engines like Tez and Hive on Tez are looking definitely in being able to do that.
One other quick question. I believe Yarn.
We need to wrap up. Last question.
Last question. So Yarn, the way it manages the capacity, I believe it's not very effective in terms of if I ask for 20 containers, it gives me 20 containers. I may not be using the 20 containers effectively. I may be using 10, and 10 are getting wasted. Are there any effort in place to look at actually how much of the containers are being used and pull it back? Like there are some third-party products available like Puffer Data and stuff doing this, but are there any Apache project or thoughts in place to take care of this going forward?
So I think I mean, within MapReduce, it's not too bad because there are some counters that you can use to do that, to figure out, oh, look, they only use this many CPU seconds or this much memory within their container, but that's MapReduce specific. I think there are some JIRAs out there to try to bring that up to the kind of the Yarn level for an application. So you can say, okay, this application launched 50 containers, each one of them used this much resource. He asked for 2 gig, he only used 1 gig. So I don't remember the JIRA numbers, but I thought there was, that's what you need to do, right, is raise it up to the Yarn level, not at the MapReduce level.
It's something like that today, I think also we do through logs. It's not built in.
Okay.
Thank you.